let's briefly recall everything we went through last week, and then let's add this week's stuff. So this week I just want to add mostly conditionals like if, else, elif, and also loops, while and for loops. So we'll see what those are and how to use them in a moment. But let's first briefly go through everything that we did last week. So this is just the code that we wrote last week. So let's go through it. So print, as you recall, just puts whatever you have here out on the screen. We can put text. We have also numbers. For numbers, we have integer numbers or floating numbers, depending on if we want decimal points or just whole numbers. And text can be just one character or a bunch of characters, it doesn't matter. And yeah, so what are the different data types? So we have strings, which is just text in quotes. We have integers, whole numbers. We have floats, which is, as you can see, just numbers with decimal points like 3.5 and such. We also have booleans. A boolean is a statement that is either true or false. So you can either literally directly write true or false, but that's not very useful. Or what we can do is we can write some statement that is maybe true, maybe false, and maybe depending on that, we want to do something. For instance, we can say 3 is more than 5, which is of course not true. So this is going to be same as just writing false. So 4 is less than 9 is true. 2 plus 2 equals 4 is true. As you can see, when we want to compare the equality, we write two equal signs, not one. So this would be wrong. We have to write it with two equal signs. We can also write just complicated thing like 5 minus 2 plus so and so on and then equals 6. And yeah, based on if it's true or not, it will either give us true or false. Now, what else? So we have more than or equals, less than or equals. We have not equals. And yeah, this is all different kinds of comparison operators. And we'll see them in examples more, and it will make more sense why we should have them. So let's get to more useful sites now. So just one thing to keep in mind also is that strings and numbers are not the same, so that even just like number one written directly as a number is not the same as it's written as a text. So if you write 1 equals 1, this will be false, but this would be true. Yeah, so we can print any text and we can have variables. So variables means that whatever value we had before, like this number or this text, we had to assign it directly wherever we're going to use it. But suppose we want to manipulate it, use it multiple times. For that, we get variables. And what variables do is that they hold on to a value for us so that we can then use it. So for instance, we declare a variable called age, and we say it's equal to 26. Now every time, instead of saying 26 more than or equal to 180 and so on, we can say age is more than or equal to 180, or name is and whatever, and I'm age years old. And what this will do is that the value of this variable will be inserted here. This allows us to reuse a lot of our logic, and also it allows us to more clearly understand what's going on in the code. So basically, by giving them clear names, we can see what we're doing. For example, here, age is more than or equal to 180. Well, I guess 18 makes more sense. And we say can drink alcohol. So what we're saying here really is we are declaring a variable called can drink alcohol, which is of type Boolean, because as we see here, it's a statement that will be either true or false. So if someone is older than 18, then they can drink alcohol, and if they're not, then they can't. That's the idea. And inside the variable, we can store a string, a number, a Boolean, or well, anything. We can also print everything on the screen. We can separate by commas, like name is like name, age years old, and it is whatever, whatever. In fact, let's run this to see what we get. Like Geo is, oh, let me actually remove this to make more sense. So here you can see Geo is 26 years old, and it is true that he can drink. Because you see name is Geo, age is just 26 years old, and it is can drink alcohol, which is in this case true, that he can drink. Now, another thing we covered last week, if you recall, is that we can also ask the user to give us their input. For instance, here you can see we say name equals input, and what is your name? So whatever we write here now will be inserted into our program. So let's say Nika, for instance, right here. And now the next question is, how old are you? I'm just going to say 22. So now it brings me here. So then it checks can drink alcohol equals age is more than or equal to 18. And 22 is more than or equal to 18, so it's going to be true. And if can drink alcohol, so if that was true, it will say you are Nika, you are 22 years old and you can drink alcohol. So you see, you are this, you're this. So this if else, the way this works is that if whatever we write here is true, then this will execute, or otherwise this will execute. So for example, if I run this again, and I say Nika, but now I say that I am 5 years old, it will say you are too young, because it went into this one. In fact, one thing we didn't cover last time, but we can certainly cover now, is we can put a breakpoint in here and we can debug our code so that we can understand what's going on line by line. So debugging means instead of your code executing all at once, it will stop whenever you tell it to so that it can look inside and see what value each variable has. So let's see what that means. Any environment you use will have its own debugger. In case of Visual Studio Code, you get that by coming here and then clicking just Python debugger. PyCharm has it slightly differently, and other ones have it differently as well, but they all pretty much have a kind of debugger. And the idea is you run your code normally, like it's still stopped here because I have to give it my name. Let's say Nika. Let's say this time I give it an age of 25. And when it comes here, it won't keep going until I tell it to keep going. And over here, we can see the values of all the variables we have. So we have age equal to 25, but right now it's 25 as a text. And can drink alcohol is true for now because we assigned it before. Ignore that for now. And we can see the name is equal to Nika because I inserted that just now. So after I execute this line, watch what will happen. Age became a number of 25. That is because previously, when we took the input always takes a string, which means that whatever you give it will be a text value. Even if you technically give it a number, like I did here, it'll be a text version of that number. So it'll be like 22 in quotes. So if you want it to be an actual number so that you can compare it, add to it, subtract or whatever, you'll have to write it like this. So int age. And so this will turn it into an integer, basically. And now age is a number 25. Now we come here and we say can drink alcohol equals age is more than or equal to 18. So we know that age is more than or equal to 18, so can drink alcohol will be true. And now here, if we can drink alcohol, we'll step in here and we'll say this on the screen. This is the main idea. All right, so far, is everything clear?
Yes.
First of all, I have some examples prepared here, but let's write them ourselves actually. So uh, yesterday's lecture, you probably covered some basics of how a neuron works, right? Like its structure and such. Now, let's slightly expand on it and let's say something like this. So every time we do anything, like when I'm speaking right now, or when we're thinking, or when we're feeling, neurons have to communicate with each other. And in order for neurons to communicate with each other, they basically have to spike. And when a neuron spikes, it sends signals to the neurons that it connects to through its synapses. Don't worry too much about understanding the details of that right now. We'll cover that in next week in neuroscience lecture. But right now, I just want to connect that to programming. So here's one thing that we should think about. So in order for a neuron to spike, it needs to cross some threshold. So let's say, for example, that in our case, some barrier is like, I don't know, minus 40, which is roughly accurate, but yeah, well, let's not worry about accuracy right now. Let's just say some barrier is minus 40, and our potential inside the neuron is right now minus 70, for instance, which is generally the resting potential. What we can say is if our potential is more than the barrier, we want to say the neuron fires. And by the way, these are letters just as much as these are letters. They're called Unicode letters. You can put them in text just fine. You can put emojis and whatever you want. So right now, the way this code works is nothing happens, as you can see, because no spike. Because you see the potential is minus 70, but it needs to be more than the barrier. Well, like if the potential was 10, then we would see that neuron fires. So this is a simple example, but now let's say, what if it's not more than barrier, but it's a different special case when it's in refractory range of like, let's say minus 85. Or even let's just say minus 70 for now. So if potential is even less than refractory range, then we'll say that neuron is in refractory period. And otherwise we'd say neuron is okay, but not spiking. In this case, we would have three different cases. And what refractory range means, roughly, is that, let me for it. So it's like this. Neuron generally rests at minus 70 millivolts of potential. When a threshold is crossed, when basically every time a neuron gets signals from other neurons, or in case of sensory neurons, if it gets signals from like eyes or ears or something, its potential goes a little bit up. And if it goes up enough, right around here, about minus 55 in this case, but it will start to shoot up very quickly, and this is called a spike. And then it will come back down. And when it comes back down, it will go undershoot, so it will go too much down, and for a little bit, we'll not be able to trigger it as easily anymore. So this period is called refractoring, and basically it just means that we cannot fire a neuron. It doesn't mean anything else. So let's see. In our case, our neuron fires normally if it's higher than the barrier. Let's set it to minus 55 to be more accurate. And if it's less than minus 70, which is the resting, that means it must be in a refractory range. So actually, let's call it resting potential. So if our potential is less than resting potential, that must mean that we are in the refractory period where we can't spike. And otherwise, we say neuron is okay, but not spiking. So in this case, we can see that for any specific potential, like minus 40 would still fire. But if we say minus 60, then suddenly it's okay, but not spiking. But if we say like minus 80, it will not tell us that it's in the refractory period, so we can't spike. Now, how does this work? Let's just go through it with a debugger. So basically, you can see that potential is minus 80, and potential is not more than barrier because this is less than this, so that's not where it will enter. But potential is indeed less than the resting potential, as you can see, minus 18, minus 70. So it will enter here, and this will be printed to the screen. This is the main idea. And by the way, to step through this, let me just do it one more time. To step through this, I can either click here or just type F10 on my laptop. Right. Anyway, this is the basic idea of if, elif, and else, and we can also chain this as much as we want. Elif and then some other condition as well, like if potential is, let's say, equal to exactly minus 60, then minus 60 is a special case. Not really. So that we can basically add as many conditions as we want, and it will trigger on whichever one is true first. We will see this basically become more relevant when we get to more serious examples. Just bear with me for now. All right. So this is the main idea between if, else, and elifs. So this is just a chain of conditions, and whichever one is true is the one that will be executed. And if, for instance, both of these are true, only the first one will be executed. That's the idea. Okay, now let's quickly review all the things I want to cover in this video. So we have if, else, and elif. I also want to cover the ternary operator. I want to cover lists, a for loop, a while loop, and random. So it might sound like too much, but each of them are small concepts. Let's go through them. All right, so let's say that it's a simple case where we just have a barrier, and we want to say if potential is more than barrier, then neuron fires, and else neuron does not fire. When you have this kind of if-else situation, where you must basically choose some text or some value depending on some condition, there is a shorter way to write this. Ternary operator equivalent. So an equivalent of writing this is, we could say print, and what do we want to print? We would say neuron fires if potential is more than barrier, or else neuron does not fire. So this is the exact same as this. So let's comment this for now. By the way, to comment this, I did control and slash. Control slash to comment out many lines. Like this. I keep this here. And so this will actually do the exact same thing, but it will do it in one line. Let's set it to -20. And you can see it fires. So basically, we can say just as a text, and we can just print the text. So essentially what this does is that if this condition is true, then we'll get this value, otherwise we'll get this value. Similarly, we could say, for example, ticket price is, let's say, 10 if some person's age, let's say we have age, which is like, I don't know, 10 years old, someone, and if age is less than 18, or else 20. And we'll just print ticket price. In this case as well, if the age is less than 18, then ticket price is equal to 10, otherwise it's equal to 20. You can see if I'm 30 years old, then my ticket price will be 20. If I'm exactly 18 years old, it will still be 20. But if I say less than or equal to 18, then it will be 10 again. So this is the main idea in ternary operator, which is that it's a shorter form of saying essentially a rather simple concept of, if we were to just say if age is less than or equal to 18, ticket price is 10, else ticket price 20, this would be the exact same as saying this. So that's it. That's the idea of ternary operator. Are there any questions?
Do we need to identify the variable first, for example, age equals 18, or we can just like do print immediately?
You mean like this?
Yeah.
If we do it like this, then the age variable does not exist. And so when we run our code, we'll get name error, name age is not defined. So in this case, because we are using an undefined variable, our code will crash. But of course, it doesn't have to be age. It can be something even directly written here. Or it can also be something defined from somewhere else, or it can be something taken from a user. It doesn't really matter where we take it from. It can also be, how old are you? Like this case, we would take it from user. I would say 15. Then your price, let's say age is less than 18. And my price for the ticket would be 10. So the idea is you have to define whatever variable you're going to use, because otherwise Python doesn't know what to do with this. Like, what is it? What's the value here? How am I supposed to, is it a number? Is it a text? What even is it? Like, Python has to know what it's comparing or what it's doing. That's why you have to define it. So you have to still give it some value. You could even say that it doesn't hold any value. So you could say age equals none. But in this case, you would get an error because you can't do the comparison then. So in that case, then you would have to say like age is not none and age is less than or equal to 18. So basically, this and or and not operations, if you remember from the previous week also. Let me see if we had them here somewhere in the examples. No, we didn't. Actually, here. Okay, there is a crime. Let me fix that right now. So in our conditionals, we can chain them such that, let's say, for example, let's say our logic is that, let's just write it like this. For people aged 5 to 15, our price is 10. For people under 5, it is free. And for people older than 15, price is 20. Yeah, let's say like that. So let's forget this age is none. For now, let's just say that age is 15 or whatever. In fact, let's just take it from the user like this. And I am converting it to an integer right away because I know that I will need it in number form, not in text form. So here we could just say, if age is less than 5, ticket price is 0. We could also say, if age is less than 15 and age is more than or equal to 5, then ticket price is 10. And if age is more than 15 or more than or equal to 15, then our ticket price would be 20. So this basically means that if both of these conditions are true, then do this, or otherwise not at all. So there is and, there is or, which is just if one of them is true, and there is also not. So not would be like if not age is less than 5, which basically means that age has to be more than or equal to 5. So these are the main three versions. There is and, or, not. These are the three operators that let us chain the logics. So that we can have, yeah, basically let's just write this again. If age is less than 5, price is 0. But realistically, we can just change like this. Elif age is less than or equal to 15, or less than 15. Price is 10, and else price is 20. And if you can notice, this is the same as writing like this. If we say it like this, if age is more than or equal to 5 and less than 15, price is 10. And if age is more than or equal to 15, price is 20. So actually, this is the same as this. And why is that? Because here we have else. Here we don't. So here, this place will only be entered if this was not true. And if age less than 5 was not true, that means that by the time we get here, we already checked that age is more than or equal to 5, which is why we don't have to write this part anymore. And by the time we get here, we already checked that age is more than or equal to 15. So this can be written in a shorter form like this. These are some of the main concepts that we'll keep going through because we'll be doing more and more tasks around them. But for now, let's keep going. And by the way, feel free to interrupt me at any moment. And as you can see here in our examples, I will send these examples to at the end of lecture. For if else elif, we had just this, let's say some stimulus is some random number. And if it's less than 3, we would print this. Otherwise, if it's less than 7, which pretty much means between 3 and 7, it would be moderate stimulus. And if it's higher, it would be strong stimulus. And here for a ternary operator, right here you can see if this number is more than or equal to that number, we'll say spike. Otherwise, we will say threshold, the rest. Yeah. Okay, now let's get into lists. Lists are basically when you want a collection of values at the same time. So sometimes we only want one value of a variable. Like we want my age to be 15. Well, let's say we have three people in our group. In that case, we might say something like age 1 is 10, age 2 is 20, and age 3 is 15, for instance. And we might want to calculate the ticket price for each of them. And so we might say whatever our logic was, right? So if age 1 is more than 5, and let's say we want to calculate total price. So in this case, we would first say maybe total price is 0. And then if age 1 is less than 5, total price just doesn't change at all. So because nothing happens, we can just say pass. Pass means nothing happens. So this means nothing happens. Else if age 1 is less than, let's say 18, then price goes up by 10. Let's say this is our logic. And else our price goes up by 20. But then if we wanted to repeat this for other ages, for other people, we would have to duplicate this code and just rewrite them to age 2 and age 3. So because in this case we had three people with different ages, but we had to do the same thing for each of them, we had to duplicate our code. Now imagine if we had 10 people, right? So our code would get unreasonably large. Like let's say age 5 is also 70, and age 6 is, I don't know, 12. In this case, our code would start to get so messy and so big that we would not be able to maintain it. So a better way that we could handle this in such case would be to say, we will create a list of ages. Let's call it ages. And we can just write 10, 20, 15, 4, 70, and 12. And then we can go through this list and do these operations on each of them. So we will say for age in ages, and this will mean that each of these will be taken one at a time and put in the variable of age, and then we will repeat that logic. So if age is less than 5, yeah, let's say, yeah, in that case, price is equal to 0. Else, if age is less than 18, price is 10, let's say, and else price is 20, for example. And then we would say total price increases by price. And then we would print the total price on screen. So in this case, we can see that it apparently goes up to 70. If I change it a little, we can see it goes up to 60. If I change this a bit as well, it again goes up to 80, and so on. So basically, lists allow us to repeat a logic on a group of variables. This is the main idea behind them. And now let's rejoin this meeting because it's about to exit. And when we rejoin, we'll dive a little bit deeper into loops. And yeah, that's basically it. Do you have any questions right now? So, as I was saying in the last moment before our call ended, a list is a collection of values. It can be a collection of numbers, or it can be a collection of strings, a collection of booleans, it can be a collection of anything. The main idea with why we would bother with lists is because we don't have to write them out like this anymore, and we can repeat the logic over each of them by running a loop through the list. This is the main idea why we would use a list. For instance, to go by the example of neuroscience, let's say that we have some neuron that will maybe fire and will maybe not fire. Let's say that neuron has a potential, starts with minus 70 even, let's say. The threshold that it must reach is minus 55. And let's see that the stimuli it receives are a bunch of numbers. Like sometimes it's a positive number, sometimes it's a negative number. So basically the neuron will either increase its potential or decrease it. And if at any point it reaches minus 55, it will spike and our code will end. Let's write the logic for that. So in this case, let's say that we have a bunch of random stimuli, like sometimes negative, sometimes positive, but generally increasing, let's say. I don't know, like this. And let's say that for each stimulus in this stimuli, and by the way, it doesn't have to be a very similar name. I can just call it for X in stimuli, but I'm choosing a name that will make it obvious what we're doing. So this is, let's say, a bunch of stimuli that will apply to our neuron to just keep increasing or decreasing its potential. So every time we will say neuron potential increased by a stimulus. And right now, our current potential is going to be this much. It's measured in millivolts, but I mean, that doesn't matter right now. And we'll also say that if our potential has reached the threshold, we should say we fired, and then let's end this. And to end running through a loop, we say break. So to make it clear what this will do, let's put a breakpoint in here, and let's keep going through it. Let me run the debugger, and we'll see what's going on. So right now, over here, you can see, what do we have? We have threshold at minus 55. We have neuron potential, which is at first minus 70. And we have a stimuli, which is just a list of numbers, you can see, so on. And at each point, a variable stimulus will get a value of some member of it. So at first, stimulus, you can see, is equal to 5. Then it will be equal to 2, then it will be equal to minus 3, and so on, as we go through each member of a stimuli. So each time, we get stimulus, in this case 5 right now, and we want to increase the neuron potential by it. So here you can see potential became minus 65. And we write that on the screen. Current potential minus 65. You can see it right here. It's not more than threshold, so we keep going. The next stimulus is equal to 2, and so our current potential became minus 63. We keep going like that. Now it will decrease by 3 because stimulus was now minus 3, and our current potential became minus 66. We can keep running like this until we get more than minus 55. Let's see, right now stimulus is minus 1, and our potential is minus 59, so it's about to become minus 60 again. Let's just keep running this for a moment. You can see that right now our potential is minus 61. The stimulus is 10, so we will finally get over the threshold this time. So you can see our potential became minus 51 because we added this 10. And so this time when we come here, our neuron potential of minus 51 will be more than the threshold, which is minus 55. And so we will enter here, and we will print on the screen neuron fires, finally, and then we will break. And what break means is that that's it, the loop ends. We don't keep going even though there were more numbers to check. This is the main idea of how to run through a loop, what we can do with it, and how to break out of it. Do you have questions about this?
No.
All right. Don't worry if not everything is obvious right now. We will have homeworks, and there we will be able to more deeply explore these topics and give you more time to reflect. But for now, let's just explain the basic ideas, and yeah, that's about it. Now, another way we could have written this so that we would not have to break ourselves is, here's what else we could do. We could, instead of writing it this way, write it like this. We could say while neuron potential is less than threshold, we could keep going. And here's how we could keep going. Let's say that this is a list, right? How many elements does it have? Like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 elements in this list. But how can we know that for sure, even if we change its size, like right now I changed it, right? How can we still be able to tell how many elements there are in here? What we can do is we can say size equals len stimuli. So len is a built-in function in Python that gives you a length of either a list or a string. So in this case, this will just give us how many elements we have. And then what we are able to do is we can access each specific stimulus, like each specific element of this list, by giving it the right index. For example, if we want to know what the first member in this list is, we can just say print stimuli at 0. So we can use this square brackets and inside write the index. And the way indexes work is the first element has the index of 0, second one has the index of 1, then 2, then 3, and you get the idea, like that. Let me just align this properly. Yeah, like this. So we can see that we have 18 elements from 0 to 17. And if we ask what the first stimuli is, it will give us 5. If we ask what the value in number 6 is, it will give us minus 20. As we can see here, 6 is minus 20. If I ask for 12, for instance, it will give minus 6 right here, as you can see, and so on. And we can also count from backwards. So basically, minus 1 would be give me the last element. So it's minus 30. Minus 3 would be right here, so it should be minus 25, and so on. So we can either count it forward or backward. We can also just print the entire list to the screen. It will just give us all of it. Or we can print a sublist. A sublist means we can start here and maybe end here. Like if we want to print just this range, we can say that we want to start at 3 and end before 8. So we will say 3 to 8. And this would give us these numbers, right? 7 minus 1, 4 minus 20, 10. So the multiple ways that we can go through it is here sublist from 3 to including 7. So this basically. First element, 5 in this case. Last element, which is minus 30. And yeah, these are the different kinds of ways we can use to access the list. We can also change elements inside the list. So one thing we can do is we can just say stimuli at 3, which is this one, right? It's 7. We can set it to equal 4 now. Now if I print the entire thing on the screen, let's print it before and after to check what's going on. We can see that it was like this. Then it still remained like that, except at this place it went from 7 to 4. So these are the different kinds of manipulations that we can apply on a list. We will dive more deeply into lists and how to manipulate them in next lectures. But for now, this is all the main understanding we need in order to introduce the while loop. Now let's say that we have some index that starts at 0. And while our index is less than size, because remember, we can't really go with size, right? Because 17 is the last element and size is 18. So if we ask it for 18th element, it will crash. In fact, let's try that right now. So if I ask it for 18th element, you can see index out of range because 17 is the last index for which it still has a value. So let's say that whatever index we access it with has to be less than the size, which is 18. So we can say, well, like, let's just say we have an index of 0, and we have neuron potential right here. And just to repeat the same logic that we had in the for loop before, we can say while our index is less than size and our neuron potential is less than the threshold, we will say that our neuron potential is increasing by the stimulus. By the way, the stimulus in this case would be stimuli at the given index. I'll put a breakpoint here so that we will understand all of this step by step, by the way. Then we'll just increase it by stimulus again and print on the screen just the current potential. And here, after the loop is over, either we reached the neuron potential crossing over the threshold and that's why we stopped, or we simply went through all of them and still didn't happen. Oh, by the way, we need to increase the index manually by 1 here. So this will mean that we first get the first element, we add it, then we get the next element and add it, and so on, until either we run out of elements by reaching the index to size, or until our neuron potential exceeds this threshold of minus 55. So let's see what would happen. So here we can just say if we indeed exceeded our threshold, we'll say neuron fired, or else neuron did, or else let's say we went through all stimuli, but neuron did not fire. All right, just to be clear about what's going on here, let's run this with a debugger. So let's see. Right here, we have neuron potential of minus 70 and a threshold of minus 55. So again, our logic is that we'll keep adding these numbers to this, and if at any point it goes above minus 55, we'll stop and we'll say that it fired. Let's move on. Size is equal to 18, as you can see, because len stimuli gives us the length of the list. And we say that an index at first is 0. So of course 0 is less than 18, and our neuron potential is less than threshold for now, so we enter. And we get the stimulus, which is 0th element of this array, which is of course 5. So as you can see right now, stimulus is equal to 5. We increase our neuron potential by that, so that our neuron potential becomes minus 65, and we write it on our screen. So current potential minus 65. Then we have to increase our index so that we get to the next element. This is something that the for loop took care of for us, so that we didn't have to bother with it. As you remember, the for loop iterated over the list all on its own. But here in a while loop, we have to do it ourselves. So we have to increase the index, then get the next element by sampling at that index and putting it in a variable. So this would repeat a bunch of times, and we can keep track of it right here. And if at any point it becomes above minus 55, we'll be done. But it looks like I made them too negative, and it might never actually... Oh, never mind. So as you can see, at some point we got exactly minus 55 at index 12 specifically. And because of that, we exited this while loop because this part no longer held. Because we said that we would keep doing this, going through the elements, as long as our neuron potential was less than minus 55. But at some point it added up to minus 55, and so we exited the loop. And we come here and we see that neuron potential is now more than or equal to threshold because it's minus 55 and it's more than or equal to minus 55. And so we will now say neuron fired. This is the main idea. Now to make sure about the other case, let's just say minus 300 so that it never has a chance of catching up. Let's just run this code. And in this case, I ran it without a debugger to make it faster. We can see that it was always very negative, and so we went through all the stimuli, but neuron did not fire. So again, this logic right here is the same as just writing it like this for stimulus and stimuli, neuron potential plus equals stimulus, and yeah, this. So this is same as this. I will also send this as an example. In fact, let me just copy this over to the examples file. And don't worry too much about understanding all of this right away. We'll have plenty of homework through which you can develop a deeper intuition. None of this is actually too difficult. It's just that it might take a moment for it to click. But this is fine. This is completely normal. You're, in fact, supposed to learn programming mostly by practice. So the real reason to watch lectures or read books about programming is to get the first idea, which is like basic skeleton, but then to actually feel it with complete understanding, you have to practice. So don't worry too much about not getting something directly. It's completely fine. Now, just one more thing I want to explain in this lecture, and then we can keep going through it to deepen our understanding, is random. So sometimes you might want to get some random numbers or random text in your program so that you can do some more unpredictable calculations or make sure that your code works for all the different cases and so on. So let's see what that looks like. It looks something like this. So first we say import random. And by the way, we will in next lecture discover how to do more complicated things like functions and such. But the main idea is that you might have multiple Python files and one might define some code, and then you might want to use that code in another file. And in that case, you'd have to write imports. In this case, random is a library that Python gives us, but we could also write our own things here and then just access them in different files. So here's what I mean. So inside this random, we have some functions that we could use. For instance, we have random.random, which will give us a random number between 0 and 1. So let's just say x equals random.random and print x. So if I run this a couple of times, you can see that each time it gives me a slightly different, or actually very different, number between 0 and 1. In fact, if I want to get just 10 random numbers on the screen, what I could do is I could say for I in range 10, we could just say print random.random. And this way we could get 10 random numbers on the screen. And by the way, I just snuck something new onto you. This is range 10, and essentially what it does is it creates a list that goes like this. So I could just say, 10 digits, and I could say for I in 10 digits, and this is just forcing the program to run 10 times, basically. It's the exact same as saying range 10. So these two are same operations. So when you don't really have an exact list, but instead you just want to do something X amount of times, you can just say for I in 10 digits. And to be clear about what it's doing, let's ignore the random for a moment and just print I. So this range of 10 is same as this. And so what this will do is it will print this out to the screen. So you can see I is equal to 0, then 1, then 2, and so on. Which means this is just running through lists and putting each element's value into this I. I could also call it X or whatever I want. We are not constrained by names. It's just that we should always pick names that make most sense. And in Python and generally in every programming language, it's sort of a standard that in a loop, if we want to index through something, we use either index or more commonly just I. So there's not any deeper meaning behind it. This letter is just more popular. That's all. So you can see that this will basically run it all 10 times, giving the different value to I each time. And what we can do is we can use this to do something on the screen 10 times. Like we could just say hi on the screen 10 times. Say hi, 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 hi. Or even just hi 0, hi 1, so on. We could also say some more complicated things, like let's say our signal is equal to a random number, and if the signal is more than 0.7, we'll print spike at I. Else we would say no spike at I. And here you can see sometimes it will spike and sometimes it won't. And this will be different and random each time. But depending on where I set this range, it will be more common or less common to spike. Like if I set it at 0.99, it might even never spike. I mean, it will sometimes, but it will be more rare. So basically, we can sample the random numbers and then do some custom logic on them, essentially. So random allows us to, yeah, basically just randomize things. So this is when we want between 0 and 1. But let's say now we want something more complicated, something that gives us a number between, let's say, 10 and 20. One moment. If we want a number between 10 and 20, what we can instead say is, let's say some value is random.rand int between 10 and 20. And we can just maybe instead say value is more than 13, because whatever. Sometimes it will spike and sometimes it won't again. So the main idea is random gives us these two main variables that we need to be aware of. So random.random gives us a value between 0 and 1, and random.randint gives us a value between just whatever two integer numbers we give. Now, just one more concept to keep in mind about randoms is that, well, they're random, which means that the same code, if you run the same code multiple times, you will get different results. But sometimes that's frustrating. Sometimes you need to be able to replicate your exact code. And for that, random allows us to seed it. Let's see what that means. So we can say random.seed with some number. We can just make up whatever number we want. And this means that as long as this random generation starts from the same seed, we will get the exact same thing every time. So let's say this is what we got, but if I run it again, you can see it's the same result. And no matter how many times I run, it will always be the same result because it starts from the same seed. So what seed basically means is that probably nothing in the universe is truly random. It always has to depend on something. If you don't specify what to depend on, it will depend on something like how many milliseconds have gone by since the 1970 or something like that, so that it's random enough for your practical purposes. But if you want to control exactly what values you get, you would write some seed. Like you might write 10, for instance, and get some different value here. But yeah, basically for each seed, every random value will repeat. Like, of course, we sampled it 10 times and each time we got a different value. But if I rerun this program, I will again get the same things. That's the idea. So the three main things to remember about random. First is random.seed with some x to make it predictable and repeatable, also known as reproducible. Second is random.random. Yep, just random float between 0 and 1. And random.randint, random integer between a and b, including both a and b. In fact, let's copy all of this in here. And let's see what else we should check here. All right. There is one more thing I want to show you about for loops. Yeah, pretty much this. So let's see that now, say that we have a bunch of neurons and each of them will either spike or not spike, depending on what their action potential is. So we say that our threshold is minus 55, and we'll say our neuron potentials are, let's say, some are minus 70, some are minus 80, some are 20, some are minus 30, some are minus 40, some are minus 65, some are minus 10, exactly minus 55, 50, 100, 200, whatever, minus 20. And so we have all these different values. And let's say we want to know which of them will spike and which of them won't. So if I want to say spikes, or will they spike, I could make an empty list and then go through each of these potentials and say, if potential is more than or equal to threshold, then will they spike will add true. Append just means add an element to a list, by the way, or else add a false. Or in fact, we can even speed this up and say append potential is more than or equal to threshold. And this way, if I print this, we will see some falses and some trues. In fact, we could even say something like, let's give it text values instead. Where was our lightning bolt thing? Right, this. So we could say either this, if this holds, or else just empty string space. So you can see sometimes they will spike and sometimes they will not. A quicker way to write this, because right now we had to create an empty list, then we had to run a for loop through these guys, and then for each of them we had to append it with some condition. So there is a quicker way to write this, and this is called an inline for loop. What it does is that we can directly say, will they spike equals something for potential in neuron potentials. Let's just say what it is, like this here, exactly. So let's delete this. And this gives us the exact same result. So an inline for loop is a way for us to basically, well, let's just simplify this for now to potential is more than or equal to threshold. Yeah, just false, false, true, true, whatever. So the idea is an inline for loop allows us to write a for loop and whatever we wanted to calculate with it into a list all in one line. So this is the exact same thing as what we did before with a regular for loop and creating a list and then adding elements to it. This is just shorter and you will often encounter this in real programs because, well, people just like to write short code. Now, as you remember, all of this is relevant because in real neuroscience and as well as any other kind of science, Python is used a lot and we often have to work with datasets. And datasets mean that there's a lot of lists, there's a lot of operations we have to do on them. And so these kinds of for loops are very common. We'll see them in the homeworks, but yeah, generally this is very common and we will get used to it with more examples. Now, another less practical but just potentially more understandable example is, let's say we have some numbers. And we need to find out the squares of these numbers. One way would be, of course, to just say for number in numbers, squares that append number times number, or number like this. But another way that is shorter and maybe better is to just say squares equals for number in numbers, just number times number. This is equivalent to this. And either way we can see in squares. And these are the squares of these numbers. So the idea is with inline for loops, we can basically win some space and make things more clearly understandable after you get used to the syntax. So the only thing that's literally annoying is that you first write the operation and then the for loop. Whereas this way, of course, you first write the for loop and then the operation. And by the way, in case you haven't noticed, in Python, we have to care about indentation. So how much space is between this. So if I were to write it like this, well, this would crash because it would think that nothing comes after the for loop. But even if I do have something here, like print number, this will be very different. Like this will give us the squares just fine. But if I write it like this, what will it do? It will only give us one thing in the list. Let's just print high to not make it any more strange than it needs to be. But yeah, basically you can see if I put this outside the for loop, it will only execute for the last value of a number which is 15. So it will only have 225. But if I put it inside, then all the values will be put in there. This is called indentation. And in Python, we have to care about it. Basically, we have to click the right amount of tabs. If I do it like this, my code will crash because it's an unexpected indentation. Similarly, if I just write a space, it will also crash. So basically, we had to make sure to use one indent for something that's inside, and then if there's anything more inside, like if number is more than 10, we need to put another indent. That's the idea. But each time we had to use one indent exactly so that our code doesn't crash. So these are all the main ideas we went through. Let's just have a review, and don't worry too much about having it all click right now, because there'll be a lot of homework. And when you go through this homework, and also maybe when you rewatch this video, because I will upload this on YouTube, basically this will start to click. All right, so here's everything we covered today. If else elif, this is that we have some number. If it's less than 3, then we will do this. Otherwise, if it's less than 7, we will do this. And otherwise, we'll do this. 7.2 is, of course, more than 7, so it will say strong stimulus. In fact, let's run this to prove this. So yeah, it said strong stimulus. Now, moving here, membrane potential was minus 65, threshold was minus 50. Potential is not more than threshold, so here we'll say rest. And instead, we got rest. Then we come here, and what do we have here? We said that we have some excitatory synapses and some inhibitory synapses. Don't worry too much about those things, but basically it means that they either add to neurons' potential or decrease it. So these are just lists. We got the sum of these values by saying sum, and sum of these values, and we got the total, and total is apparently 1.6. We did a similar thing here, just sum them up, just add them from this. We did a similar thing here, but just got the index as well. I'll give the example, so don't worry too much. We got the while loop, and we did the random numbers. So this is every topic that we needed to cover for now. I will upload this file. I will upload some references as well and some homeworks. And that's it for our today's video. So don't worry if you feel that this is a little bit dense, because we'll have plenty of review time, plenty of homeworks, and also next lectures will again cover this topic.